Last time we started the free convection chapter, okay, and we started and we determined that for free convection we have another number based on which we decide that whether it is or if in case of the free convection, the Nusselt number does not depend upon Reynolds number and Prandtl number, rather it depends upon Grashof number and Prandtl number. And the Grashof number has a formula, and we discussed this formula. This is the formula for the Grashof number, and where this beta is basically volumetric thermal expansion coefficient, and in the end it comes out to be beta is just reciprocal of mean film temperature in Kelvin. And so we have G beta Ts surface minus T infinity L cube by mu square. So this is the formula for the Grashof number, which is used in the free convection other than the Reynolds number. Reynolds number was there for forced convection. For free convection, we use the Grashof number. Other than that, how to determine if the flow is laminar or turbulent? We have another number, and that is the Rayleigh number. So Rayleigh number is basically what? It's the Grashof number multiplied by the Prandtl number, where Prandtl number is mu upon alpha. Okay, and this is the Rayleigh number, and the critical Rayleigh number is 10 raised to power 9, 1 into 10 to the power 9. So if it is less than that, laminar; if it is more than that, turbulent. Then we discussed about the correlations and said there are 3 sets of correlations, but all are okay given the conditions for these correlations. For example, the first one is the correlation where you have, for laminar you have value of CNN, for turbulent you have value of CNN. Okay, so you have to check the condition if you are applying this equation. Okay, and then for the laminar flow there is another equation, and this is another third equation which is both for laminar and turbulent. And I told you, if it is not specified, then you are free to use any correlation you want. Just make sure that it is for that condition for which you are using. That's it. Okay. So now we were about to start a numerical problem related to it. So let's start with the numerical problem related to it. So these correlations are basically for vertical plate. These 3 sets of correlations are for vertical plate. So suppose this is the plate and this is heated, say 70 degree, 80 degree, outside temperature T infinity is 24 degree, 25 degree. So obviously if it is heated, so a boundary layer will be developed and the air will get heat up, will move up. Okay, so there will be a flow because of the heating of the fluid, because of this heated plate. So for the vertical plate, these are the correlations. For the vertical plate, these are the correlations. And obviously you are using L here, so L is the length in the direction of flow. So if it is heated, so what would be the direction of flow? The direction of flow will be up, right? So L will be the length of this plate. Okay, so if it was placed perpendicularly, then L will be the width, always in the direction of the flow. Okay, so now let's study this problem. we have a glass door fire screen used to reduce exfiltration of room air through a chimney. You know what's a chimney? Chimney sometimes in the houses, you want to keep the house warm, so there is a fireplace separately. You don't see this here because there is a lot of warm already present, but in cold areas, people used to have, or they have chimney in their home.
I have one.
You have one?
4.
4 chimneys in your home?
Yes.
Why? You want more heat?
Yeah.
Okay, anyways. So this is a chimney. So we have in a home they have a chimney, and but they don't want really, because the home temperature is maintained at 23, 24 degree, whatever, by the AC. So they don't want all the air to flow out of the chimney. Okay, so they put a glass screen in front of the chimney. So here is the fire, this is a chimney, and a glass screen is put here. Okay. So to reduce exfiltration means, infiltrate means going in, exfiltration means going out. So you don't want the home air to go out. Okay. Of room air through a chimney, it has a height of 0.71 meter, so that's the height, 0.71 meter, and a width of 1.02 meter, width is inside 1.02 meter, and reaches a temperature of 232 degrees centigrade. So this glass door, this reaches a temperature of around 232 degrees centigrade. Okay. If the room temperature is 23 degrees centigrade, estimate the convection heat transfer from the fireplace to the room. So obviously you have a fireplace, and you have a glass door in front of the fireplace, and this glass door is at 232 degrees centigrade. There is room quiescent air at 23 degrees centigrade, but there will be some heat transfer. The heat transfer will be because of 2 reasons. It will be because of the radiation as well as because of the convection, but not forced convection, because it's not the moving air, it's the stationary air. It will be because of the free convection. Okay, so what we are concerned is how much is the convection heat rate, how much is the convection heat transfer. We are not concerned about the radiation heat transfer right now, but we want to know that how much will be the convection heat transfer from the glass to indoor. Okay. So in order to determine that, we have the formula is Q is equals to HA delta T, right? So that will be the convection heat transfer. Okay, delta T will be what? We have Ts minus T infinity. T infinity is, so delta T will be Ts minus T infinity. T infinity is known, Ts is known. Area will be width multiplied by the length, or height, you can say. Okay, so that's the surface area across which heat transfer is going. Okay, so this is also known, because you know what is the height, you know what is the width. Okay, now the only thing left is this H. If you know what is the heat transfer coefficient, then you can find what is the heat transfer rate. As simple as that. Now, since we know that this is not a free forced convection, this is a free convection. So now we have to use and this is a vertical plate, free convection. So now we have to use the correlation for the vertical plate. But the correlations are depending upon if it is laminar or turbulent. So the first important parameter will be to determine whether the flow is laminar or turbulent. Okay, and before that we need to find out all the properties. Now in this case, all the properties will be taken at the mean film temperature. So you have Ts, you have T infinity. So mean film will be the average of Ts plus T infinity divided by 2. Okay. So at the mean film temperature, we have all the properties K, mu, alpha, Prandtl number, and beta. Beta is just reciprocal of mean film temperature. Okay. So now we put the formula for the Rayleigh number. Okay, we put the formula for the Rayleigh number, because based on the Rayleigh number we will decide if it is turbulent or if it is laminar. Okay, so formula for Rayleigh number is this. This formula will be there with you in the book of formulas. Okay, so here we have G 9.81, beta 1 upon TF, but TF should be in kelvins. Okay, so if you put it in degrees centigrade, it's a mistake. Okay, so that comes out to be this. Ts minus T infinity multiplied by L cube. A length will be which length we are talking about? That will be the height. Okay, that's the direction of flow. So L cube divided by alpha and mu. All these properties are known. So based on that, we find out that the Rayleigh number is 1.813 into 10 to the power 9. Do you think it's laminar or turbulent?
Turbulent.
It's turbulent, because 1 into 10 to the power 9 is the critical. Greater than that, so 1.813 is greater than 1. So this is the turbulent flow. Anyway, since this is turbulent flow, so you have what options for equation to use? You can use this equation, or you can use this equation, but this you cannot use. This is specifically for laminar. So if somebody use this one with the turbulent condition, I will not make it wrong. If somebody use this one, I will also not make it wrong. But if somebody use this one for this case, then I will make it wrong, because this is for laminar and your case is turbulent. Okay. So anyways, so they have used this one. Okay. Actually, between this and this, it's a bit more accurate than this one, but still, if it is not specified and if somebody use this one, I cannot make it wrong.
Why is this accurate more?
This one was made for larger number of experiments, for larger number of data points. Okay, so this is a simplicity form of equation. Simplicity form of the equations are easy to use, but their accuracy level is many times is comparatively less. Anyways, so they have used this equation, the third one. It just used Rayleigh number. You already know the Rayleigh number, you already know the Prandtl number, and that's it. All our rest are just the numbers. Substitute values and find out the Nusselt number. So the Nusselt number comes out to be 147. What's the unit?
Number.
It's a number, no unit. Okay. So once you know the Nusselt number, you can find out what is the heat transfer coefficient, H. Again, you will use L as the height. And once you know H, then substitute it here, and you will know what is the heat transfer. As simple as that. It's the same thing. What you are now going through is the same thing. You have the correlations, just need to know how to use them, when to use them. That's it. Okay, and find out what is the heat transfer rate.
Nusselt number equals HL upon K.
Yes. So any question in anything that you don't understand in the solution of the problem? It's straightforward. It's really not that much complicated. Okay, so let's move ahead. Now that was for the case of the vertical plate. Okay. Now if the plate is not vertical, let's say the plate has an angle. It's an inclined plate. Okay. So suppose if the plate is like this. If the plate is like this, and the plate is cool. So what will happen? At the bottom side, you will have streams of fluid which will be going down, and at the top side, you will have a boundary layer developed and the fluid is going down as like that. If you have a cold plate, right? Say inclined. If you have a hot plate inclined, the similar thing will happen but in the opposite direction. So you will have a boundary layer develop at the bottom side or at this side, and you will have streams of fluid going up at the top side. So if you see here, this thing is very similar to this thing, and this thing is similar to this thing. Okay. Similarly, if you have a completely horizontal plate, so for the horizontal plate, if the plate is cold, then you will have streams of fluid going down at the bottom. Okay, and if the plate is hot, then you will have streams of fluid going up from the top surface. Now the thing is that here the convection coefficient can be determined from the vertical plate relations by replacing G with G cos theta.
G as well.
So you remember in the Rayleigh formula equation you have a G here. G is the gravity, 9.81, acceleration due to gravity. So if the plate is not vertical, if the plate is inclined, then by just putting G, instead of G you put G cos theta, you can use the same equations for the vertical. Just the thing is that only Rayleigh number will change. Is it clear? So suppose the plate is inclined like this a little. Okay, so you know what is theta. So you will use G instead of G, G cos theta. Now solve it as a vertical plate. Okay. So you find out the Rayleigh number. Based on the Rayleigh number, you find out which formula to use, and then use the equations, empirical correlations for the vertical plate. So now you can, but there is a condition here. The condition is that the theta should be within this range, 0 to 60 degree. If the theta is not in this range, suppose if the theta is 75 degrees or 65 degrees, then this is not applicable. Then we cannot use this methodology. Is it clear?
So we can solve it.
Hmm?
How we can solve it?
It's the same way. Okay, if theta is greater than 60, then you cannot solve it using this methodology. Then there are different correlations for it. But we are not studying them right now.
Isn't here in this figure? The fluid comes from down or from where?
That's the thing in the free convection. The fluid is not coming from anywhere. Fluid is there. Like for example here in the room, the fluid is here. It's not coming from anywhere. But if I have a heated plate, automatically there is a rise of fluid. If I have a cold plate, automatically the fluid will move down. That's the thing. That's why Reynolds number is not applicable here, because in the free convection there is no fluid motion, external fluid motion. The fluid motion is because of the buoyancy effects. That's it. Is it clear? So we can solve the case of the inclined plane as well. Only the thing is that, only difference is that you have to put instead of G, G cos theta. That's it. And you can.
You say that the cold air comes down, right? But when you go to airplane up, the temperature decreases.
Oh, you're saying that within the atmosphere, why does this not happen, that the cold air comes down and the hot air goes up? Yeah, this happens.
But outside, maybe minus 20.
Yeah, but this happens. Do you know why this wind is blowing? You know wind energy. Wind energy is also the form of solar power. Why the wind blows? Because one part of the air goes hot, it moves up, the cold one takes in its place, and when the cold one is taking its place, it's a huge wind which is blowing. This thing is happening at the same time. Okay, but the thing is that when it reaches at the top, then it loses a lot of energy, okay, and it becomes cold. There are many factors behind it. We are not going to discuss those factors here, but this thing is happening. This thing is happening on the larger scale. Now suppose if we have the horizontal plate. So we covered the case for the vertical plate and inclined plate if the theta is not greater than 60 degree, if it is within 60 degree. So we covered that. But if it is a vertical plate, if it is a horizontal plate, okay, then we will have a separate set of correlations. So if it's a horizontal plate, suppose if the horizontal plate is cooled, then at the top of the plate you will have flow like this. Streams of the fluid is going to come and fall at the sides of from the sides of the plate, if it is cold. And at the bottom it will be like this, streams of the fluid going down. If the plate is hot, then at the top surface, streams of the fluid will be going up, and at the bottom of the plate, stream of the fluid will come in contact with the plate, become hot, and then move from the sides. Okay. So if you see here, for the Assalamu alaikum. So if you see here, for the case of cold plate, the top surface of the cold plate will have a similar kind of flow pattern as the bottom surface of the hot plate. And the bottom surface of the cold plate will have a similar kind of flow pattern as the top surface of the hot plate. So we have one set of correlations for these two cases and another set of correlations for these two cases. It's clear? Because you see the similarity here and see the similarity here. So we will have two sets of correlations, one for this case, one for this case. Okay. So now, if for the upper surface of hot plate or lower surface of cold plate, upper surface of hot plate or lower surface of cold plate, if this is the case, then the correlations are this, based upon the Rayleigh number. If the Rayleigh number is between 10 to the power 4 to 10 to the power 7, this. If Rayleigh number is between 10 to the power 7 to 10 to the power 11, this.
Rayleigh number and Prandtl?
Rayleigh number and Prandtl number, yes. Okay. And if for the other case, is if it is the top surface of the cold plate or the bottom surface of the hot plate, lower surface of hot plate or upper surface of cold plate, then this is just this one correlation. So you have to apply these correlations, all at the mean film temperature. This whole chapter is at mean film temperature. So let's have another numerical related to it, and we're going to complete this chapter. Airflow through a long rectangular heating duct. So you have a heating duct which is long, rectangular. So it's kind of a rectangular pipe, lengthy rectangular pipe. That is 0.5 meter wide, so the width is 0.5 meter, and 0.3 meter high, so height is 0.3 meter. Maintains the outer duct surface at 45 degrees centigrade. So the whole surface of the duct is 45 degrees centigrade continuously. If the duct is uninsulated and exposed to air at 15 degrees centigrade, so this duct is in an air which is 15 degrees centigrade, okay, and it is uninsulated, so heat will go out of it. in the crawl space beneath a home, what is the heat loss from the duct per meter of length? So you have a duct, very long duct, length is not given, very long duct, and duct is rectangular, its dimensions are given, and air is passing through the duct. So the duct temperature is 45 degree. The whole surface of the duct is at 45 degree, but the atmosphere from where this duct is passing, it is at 15 degree. So obviously, since the atmosphere is cold compared to the duct, so there will be heat loss. Okay. So now we need to determine that how much is the heat loss per meter of the duct length. Length is not given, but said that per meter how much is the loss of energy. Do you understand the problem statement? Okay. Now interesting thing is that in this duct is a rectangular, it's rectangular duct. So it has two vertical sides and two horizontal sides.
So we use 4 times by 200.
So you will have a heat loss from this side, you will have a heat loss from this side, you will have a heat loss from the top, you will have a heat loss from the bottom. Okay. So you will have heat losses from all 4 sides, so it's like 4 problems. Right?
Make it translated.
Okay, then we'll provide you the resistance of the insulation. Okay. So we will determine the mean film temperature. The mean film temperature is the average of the duct temperature and the outside temperature. Okay, and we'll find the properties at the mean temperature. All the properties. Okay.
The inside temperature is what?
45. Inside temperature is not, the duct surface is maintained at 45 degree.
Oh, so we consider with the surface and outside.
So yeah, surface and outside. Okay. So now the very first thing is to determine, okay, so this is your duct. This is your duct. Okay. So let's first consider about the sides, the vertical plate. Okay. So for the vertical plate, the first thing is that we need to see what is the Reynolds, not the Reynolds number, what is the Rayleigh number. Based on the Rayleigh number, we will decide if it is laminar or turbulent. Okay. Now tell me, what would be in the Rayleigh number formula? Everything is simple, except tell me what will be the length.
The height.
The height.
Thickness of the
Thickness of the duct. Because if the duct is like this, so where will be the flow? How will be the natural flow? So it will be heated up and the flow will be up. So the length in the direction of the flow is the thickness. Is it clear? So the length here would be the thickness here. Okay. So the thickness here is, so they determined it first keeping L as the same, and then they put L as 0.3. Okay. So if they put L as 0.3, so the Rayleigh number comes out to be 7.07 into 10 to the power 7 laminar, because 10 to the power 8 is the critical. 10 to the power 7 means laminar, right? Now if you have the laminar condition, now what formulas can you use?
The first
Yeah.
First or second?
So you can use all 3. This one is for laminar, this one is for all conditions, this one you have laminar and turbulent. They use this one, but if anybody use any of the 3, I will not make it wrong. Okay? Because
But different answer.
yeah, obviously answer will be different. Because these are all the approximations. So one guy suggesting a correlation, so his approximation would be a bit different than the other one. Okay. So in the book they have used this one for laminar flow. But if somebody use even this one, I will not consider that wrong. If somebody use this one with the laminar condition, I will not consider that wrong. Okay.
But if we use the first one with the turbulent condition,
Then it is wrong. So always the important thing for you, yeah. So important thing for you is to make sure that you do understand where to use, when to use, what correlation, under what conditions. This is the thing. Okay. So let's go back to the problem. Now they have used the second one, which was specifically for laminar. Okay, and now it needs Rayleigh number, Prandtl number, both you know. Okay, substitute the values, you will find out the h. Now this h is for the side, for both the sides, because the h for this side and the h for this side will be same. Okay, so it comes out to be 4.23 watt per meter square Kelvin. Okay, now this thing is okay, done. Now for the top plate and for the bottom plate, you will have different set of correlations because these are now the horizontal plates.
yes.
Okay, but both have a different kind of flow arrangement. For the top plate, when it is heated up, so we will have streams going up. For the bottom plate, when it is heated up, you will have streams from the bottom coming and going from the sides, right? So you have different correlations for the top plate and for the bottom plate. Now, the top plate and bottom plate, now for the top plate and bottom plate, you have to use these correlations. This is very clear. But the question is that before that, you first need to know what is the Rayleigh number, because based on that you will decide which one to use. Based on this you will decide you have to use this correlation or this correlation. Okay, for this case, okay, it's not needed, but still you need Rayleigh number to put it in the formula to get the Nusselt number. So Rayleigh number in any case is needed. Okay, now the question arises, how do you determine the Rayleigh number? The formula for Rayleigh number is the same. Okay, but here again the problem comes, what is the L?
Hi.
Yeah, you see you see it in the slide, no? But yes. So the formula for Rayleigh number, the formula for the length here will be, because you see here, what is the flow direction? Flow direction is perpendicular to this, right? So the formula would be surface area divided by parameter. That will be the formula for the length. So L will be surface area by parameter. Okay.
Why?
So just consider this as it is, because I don't have a specific answer for why, because here the flow is perpendicular to the surface. Okay, so the length should be considered as the length all along. Okay, because along all this surface it is moving in the perpendicular direction. Otherwise we cannot consider, because in the flow direction there is no surface at all. It's all perpendicular. There is nothing in the flow direction. So they will so the length here will be considered as surface area over parameter. Now here the parameter will be the boundaries across which the heat transfer is occurring, and surface area is the area across which heat transfer is occurring. Okay, now the question is that what will be this formula? Okay, so can you tell me what will be AS here? Okay, so what will be surface area? Let's, for the bottom or the top, it will be same. So what will be the surface area? So if this is W,
0.5 times L.
so W
WM
times
L.
L, right? So that will be the surface area. And what will be the parameter?
2W plus 2L.
2, or I can say 2W plus L, right? Do we know the length?
No.
We don't know the length. Okay. So now they use an approximation. Now what is the approximation? Let me tell you the validity of the approximation. Suppose I have two numbers, 10,000 and 0.1. If I add 10,000 with 0.1, what will be the answer?
10,000.
10,000.1. If I have two numbers, same numbers, 10,000 and 0.1, if I multiply them, what will be the answer? 1,000. When I add them, do you think there is a significant change in answer?
No.
When I multiply them, do you think there is a significant change in answer?
Yes.
Yes. So if one number is big and other is very small, then when you add them, there is no significant change. Even if I remove this, it's almost the same. 10,000.1 is almost the same as 10,000. But 10,000 is not the same as 1,000. So in the multiplication, big number and a small number both matters. But in addition, very small number does not really matter. It will not really make significant change in the answer. Agree?
Sure.
So see here, we have width which is comparatively very small to the length. But here it is in multiplication, we cannot ignore it. But in case of addition, we can ignore width. So if I ignore here the small number, still it does not make much difference. Okay? So if I ignore here width, then it becomes 2L, LL will cancel. So now my characteristic length will be W over 2. Do you understand the approximation which we make? Okay. So when you have two numbers, one big, one very small, if you add them, the answer will not be significantly changed. But if you multiply them, the answer will be significantly changed. So you can ignore it when you are making an addition, but you cannot ignore it when you are making a multiplication. Okay? So this is an approximation, obviously. Approximation means it's not 100% accurate. There will be some error. But the error is manageable. It's understandable, ignorable. Do you understand it? So from here we come up that L is equals to AS by P, which is approximately equals to W by 2. W is something that we know. So we know what is L here. So this thing was actually done in one step in the book, directly. But there is a logic behind why they had done it. Do you understand it or not? Zahrani?
Yes, I understand.
There is still processing something in your head. Okay. So now if we know L, now we can again find what is the Rayleigh number. Okay. So Rayleigh number here will be 1.38 into 10 to the power 8. So what do you think? Laminar or turbulent?
1.3.
Turbulent. 1.38 into 10 to the power 8. Laminar or turbulent?
Turbulent. No, laminar.
بدنا
على شيء يا أخي هذيك.
Actually the thing is that for this case we have two different correlations. One correlation is between 10 to the power 4 to 10 to the power 7. Other correlation is between 10 to the power 7 to 10 to the power 11. It doesn't matter whether laminar or turbulent. You have to use one of the correlation which fits for that Rayleigh number. Okay. So for the upper surface of or lower surface of the hot, no, we have to use this one. Upper surface of the upper surface of the hot plate, this one. Okay. For the upper surface of the hot plate, which of the correlation we will use?
The
Second one, right? This one we will use. And the lower surface of the hot plate, which we will use? This one, lower surface of the hot plate. This is just one correlation. Okay. So we will use this and this. clear? So from this we will have the heat transfer coefficient at the top side. Again, for this you have the Nusselt number, okay? So Nusselt number is basically what is is H L upon K, but L will be what? W by 2. W by 2, the way the thing that we already determined for the top plate and for the bottom plate. So anyway, so we have the heat transfer coefficient for the top plate, we have the heat transfer coefficient for the bottom plate, and it comes out to be this and this. Okay. Now we need to know that how much is the heat transfer overall. So overall heat transfer will be what? Q is equals to H A delta T for sides, two sides, plus H A delta T for top plus H A delta T for bottom. This is clear? So you have the heat loss from two sides and the top and the bottom. Now H's for the sides are known, H's for the top is known, H for the bottom is known. Right?
Yes.
Okay, area, surface area for the side, what will be?
So if you want the heat loss per unit of length, not area.
Again, that will be the approximation of the length.
No. WL. For the side, what is the sides here? No, for the side it is H
H by L.
H by L. They said H, right? This is H. Okay. The side will be so area will be H by L, right? For the sides. For the top, area would be for the top
W by L.
W.
L by W, right? So L by W. For the bottom, okay, L by W. Okay, delta T. Will it be changed for the three cases? It's same. Ts minus T infinity, right? So we know delta T, delta T, delta T. Now here we do not need Q total heat, we need Q per unit length. So let's do it per unit L. So L here will cancel, L here will cancel, L here will cancel, right? So now we know everything. I will find out what is the Q per unit length. So if we do this, altogether it comes out to be 234 watt per meter. This question was easy but was not really that much straightforward because of the L. You had different L for different cases. For the case of the vertical plate, L was the height. For the case of horizontal cases, top and bottom, L was W by 2. Then you had to use different formulas for these sides, and then you have to add them all together, heat transfer, in the end. So it was easy but not that much straightforward. But anyways, do you understand the problem? Solution, anything in it that you don't understand, you can ask. Good.
I have a question.
Yes.
Not in this slide, for the upper and lower level.
This one.
The second condition, the roll number is more than this number, and it's not in the range. It's
Then you
valid?
can, no, then it's not valid, then you cannot use it. If this is the case,
Okay,
if this is the case, then you will only write your answer that the equations available does not support this Reynolds number. Sorry, Rayleigh number. It's not the Reynolds
Should
number.
always be support something.
Okay.
At what?
So suppose, let's say, if I give a question in the exam, and you are supposed to find out the Nusselt number for the lower surface of the hot plate, and the Rayleigh number is coming out to be 10 to the power 10. Okay. So if you use this equation, it will be wrong. But you do not have any equation for it. You do not have any equation. So you'll just simply write that you do not have the equation, because the equations that you have, I did this thing not for this course. Empirical correlations, long horizontal cylinder. Okay, so we studied what? We studied the vertical plate, if it is inclined, horizontal plate. These are we studied all the plates. If we have a long horizontal cylinder, okay, so if the cylinder is heated up, then we'll have the flow across it like this. You want a break of 5-10 minutes? So we did for the plates. Similarly, now we have a correlation for long horizontal cylinder. So if you have a pipe, long pipe, heated pipe, okay, so there will be free convection across the pipe, and it will be like this, and the Nusselt number for it will be given by this equation. Nothing new in it. So you have, so this is applicable for Rayleigh number less than 10 to the power 12. So if Rayleigh number is less than 10 to the power 12, it is applicable. For greater one, you don't have the formula.
Or this formula with the random number or the Rayleigh number, I'm sorry, was given also Rayleigh number less than 10 over 12.
Yes, yes. I don't suppose, or I don't want you to remember these things. What I just want is that you should know how to use it. That's it. As engineers, you should have the skill to use it. That's it. You're not testing your memory, just testing your skills. Okay. So we have this, and this correlation is basically Churchill and Chu correlation. So it was the two guys, Churchill and Chu. How did this work? Then you have that was for the cylinder. Now suppose you have a sphere, and you have a free convection across the sphere, heated sphere. Okay, so for that, if the Rayleigh number is less than 10 to the power 11, then this is the correlation. We don't have any numerical in the classwork problems related to the long cylinder or the sphere, but you have something there in the homework. Okay, but the application is exactly the same as you had done for the flat plate. Okay, first find out the Rayleigh number, then substitute in the Nusselt number, find out the heat transfer. That's it. Okay. Now, these were all for the free convection. If you have, we discussed that if you have Grashof number divided by Reynolds number square is very smaller than 1, then this is forced convection. Free convection is negligible. If Grashof number divided by Rayleigh number square is much greater than 1, then it is free convection. Forced convection is negligible. Okay. But if it is approximately equals to 1, then it's a combination of free and forced convection. Okay, then it's a combination of free and forced convection. So suppose you have a heated plate, let's say this is a vertical surface, and this is at 400 degrees centigrade, and I also make a small flow across it. Okay, so I'm making, let's say I put a fan, small power fan, which will making a small flow. So there is some forced convection here, but because the plate is too much heated compared to the atmospheric temperature, there will also be flow. So because of that, because of the free convection, so it will be a combination of free and forced convection. Okay, so buoyancy effect will be there along with the force convection which we are doing, force flow. So if this is the case, then it's a combination of free and forced convection. Okay. So if you have a combination of free and forced convection, then you will solve free convection separately, forced convection separately. So first consider the problem as a free convection, solve it as free convection. Then consider the problem as forced convection, solve as forced convection. Both separately, then combine them together.
Plus, yeah.
But it's not a simple plus.
Why?
It's Nusselt number combination power n is equals to Nusselt number by free convection power n plus Nusselt number, forced convection power n plus or minus Nusselt number natural convection power n.
When it is plus, when it's minus.
When it is plus, when it is minus. That's a good question. Look, if I make the fluid to flow like this, okay, that's my forced convection, and this is a heated surface. So the buoyancy effect will also make the fluid to move up. So both motions are up, then it's plus. Suppose if I'm making the fluid to move like this, but this is a very cold plate, let's say minus 20 degrees centigrade. So what will happen because of it? The buoyancy effect will cause it to move down. So now the two motions are opposite. Then it's minus. Okay. So if I'm making the flow to go like this, down, that's my forced convection. But this is a heated plate, so the buoyancy effect will cause the motion to go up. That's a minus. So then you have to see the direction of flows. But now that's the determination of plus and minus. But once you determine plus and minus, then it is not just simple addition. It is power addition. This power n plus or minus this power n is equals to this power n. Now what will be the value of n? The value of n, the best correlation of data is often obtained for n equals to 3, although the values of 7/2 and 4 may be better suited for transverse flows involving horizontal plate and cylinders. So 3 could be considered as the value of n. But anyways, I did not put any problem for it in the classwork or in the homework for the combined flows. It was just for your knowledge. Okay. Because this makes it a bit more complicated. It's like a combination of chapter number 7 and 9 together. Okay. 7 was external flow, and 9 is the free convection. So, okay, convection mass transfer. There is also no numerical problem related to it here for this, but as you know, when you have the mass transfer problem, it's the same analogy as the heat transfer. Okay, but only some terms get changed. So you remember Prandtl number changed to Schmidt number, Nusselt number changed to Sherwood number, right, in the forced convection. Now we'll have similar. So you have the Grashof number, right? Grashof number was the one which we were using for the free convection. Okay, so Grashof number had this formula. Where is the Grashof number? That was the formula for the Grashof number. Now here you had beta into temperature difference, right? Beta into temperature difference. Now there, if you have mass transfer and let's say there is no temperature difference, it's just because of the concentration of two different bodies, two different species, the transfer is occurring. Okay, so there is no temperature difference. So this term beta into Ts minus T infinity will be changed to delta change in concentration over mean concentration. So rho s minus rho infinity divided by rho. This is instead of beta into T minus T, Ts minus T infinity. That's the thing. Okay. So then the Grashof number remains the same as it is before. Okay. We know that Sherwood number was a function of Reynolds number and Schmidt number, but now there is no Reynolds number. In free convection you have Grashof number. So now Sherwood number will be a function of Grashof number and Schmidt number. Schmidt was related to Prandtl. Prandtl was the case of heat, Schmidt is the case of mass transfer. Okay. So anyways, we also do not have any problem related to this topic, either in homework or in classwork. Okay, we are just discussing this topic. So with this, we complete our chapter number 9. Okay, and you have the homework problems there, so you can make solution for that. So free convection is now over. So we started with the convection, introduction to convection, then external flows, then internal flows, then free convection. So we are done with this. Now chapter number 10 is about boiling and condensation. Boiling and condensation is a phenomenon. Throughout what you have, chapter 10. Oh, I'm sorry. So chapter 10 is regarding boiling and condensation. Now throughout what you have done from chapter number 6 till chapter number 9, there was no phase change. It was all liquid or all gas. If the air is flowing, it's air.
Yes.
If water is flowing, it's water. All. There was no phase change. The difference is that in boiling and condensation, you have a change of phase. So there is a boiling curve, which is, mark my words, which is very, very, very important. There is a boiling curve in chapter number 10, which is very, very, very important. And for that, I have found on YouTube a very good video. That video is only 5 minutes. And as a starting of chapter number 10, I would just like you to silently watch the video. Okay, so we are going to just watch this video of 5 minutes regarding the boiling curve. It's a very good video made, I don't know by who, but I found it and it's good. So let's watch this video, and this is a very important boiling curve. Okay. So no, here, pool boiling.
Draw the pool boiling curve. We know that pool boiling is a mode of boiling where the fluid is stationary in the beginning with respect to the heating surface. To understand this boiling, let's consider an example of vessel containing some water placed on a burner. As the heat gets transferred from the bottom surface of the vessel to the stationary water, it starts rolling up and down. Then bubble formation takes place. And after some time the water gets boiled. This process is a pool boiling process. Pool boiling takes place in different stages. They are pre-convection boiling,
Very important. Huh? This.
nucleate boiling, transition boiling, and film boiling. These different stages can be easily plotted on a heat flux temperature plot. X-axis represents the difference between the current temperature and saturation temperature of water, which is represented by delta T excess. And y-axis represents the heat transferred to the water per unit surface area of the vessel, which is represented by heat flux Q dot boiling. The curve OABCDE is known as the pool boiling curve of water. Here, curve OA represents the stage free convection boiling. Curve ABC represents the stage nucleate boiling. Curve CD represents the stage transition boiling. And curve DE represents the stage film boiling. Now let's understand each section of the curve one by one. Let's discuss about curve OA, represents the stage-free convection boiling. When we light the burner, heat transfer takes place between the vessel and water due to free or natural convection. We can see that the values of heat flux and delta T excess start increasing. And when the temperature of water reaches its saturation temperature, that is when delta T excess attains a positive value. Then boiling takes place. This stage of boiling is known as free convection boiling. Curve ABC represents the stage nucleate boiling. As we can see, nucleate boiling is divided into two parts. Curve AB represents liquid entrainment, and curve BC represents critical heat flux. Now first, let us understand liquid entrainment. Due to continuous heating, we see that the value of delta T excess increases, and the bubbles are formed at the bottom surface of the vessel. These bubbles move upwards and carry some water along with them, but they collapse after covering some distance in the water. This is known as liquid entrainment. We see that the disturbance caused by liquid entrainment in the water increases the heat transfer coefficient, so the heat flux also increases. In curve BC, we see that as delta T excess further increases, the bubbles start forming at a faster rate. These vapor bubbles move upwards and merge to form numerous continuous columns of vapor in the liquid. The bubbles in the column then move upwards to the free surface, where they break up and release their vapor content. Due to this, the heat flux attains its maximum value, known as critical heat flux. Thus, the complete stage of boiling from A to C is known as nucleate boiling. Curve CD represents transition boiling. When the vapor of delta T excess increases beyond the critical point, we see that the heat flux starts decreasing. This is because a large fraction of the heated surface of the vessel is covered with a vapor film. This vapor film acts as an insulator as its thermal conductivity is lower than that of water. Thus, the value of heat flux attains its minimum value. Point D, corresponding to the minimum value of heat flux, is known as Leiden-Frost point. In curve CD, both nucleate and film boiling takes place partially. Thus, this stage is known as transition boiling. Curve DE represents the stage film boiling. We see that after the transition phase, the delta T excess further increases, due to which the vessel surface is completely covered by a continuous stable vapor film. Now, because of high temperature, we see that the radiation heat transfer takes place between the heated surface and the water through the vapor film. Thus, this stage is known as film boiling.
That's it. This is one of the most important curve. The pool boiling curve is one of the most important curve, and it has many stages. So this is a video, you can watch it again and again whenever you want. But this, I found it on internet. It was made excellent with.
Same name for pool.
Yeah, this pool boiling curve, same name. Okay, so this is a very important curve, and you need to understand all these stages, from point O to A, then A to B, B to C, C to D, D to E. What is happening and why is it happening? This video explains two things: what is happening and why is it happening. So this is something, the curve itself and what is happening and why it's happening, and the names: Leiden-Frost point, critical flux, onset of nucleate boiling. These things are all important for the short questions point of view. So consider this video as very important one. Okay, anyways, that's it.
Thank you.